Good evening all, and welcome to today's last section of the symposium. And our first speaker is Debapriyo Chowdhury, and he will be talking around the title Bootstrapping String Model with Entanglement Minimization. And over to you. Thank you.
Hello. Is this audio? Hello. So thank you everyone for being here, and thanks to the organizers for organizing the symposium. So I will be talking about bootstrapping string models with entanglement minimization. So here goes. So this is work with my senior Faizan Bhatt, Arnab Saha, and my supervisor Anindya Sinha. So here's my outline. I will give some motivation of our work. Then I will make a key formulation about crossing symmetric dispersion representations. Then I will move to entanglement minimization, and then I will show some results. So here's the motivation. So in 1968, these people, Dolan, Hoare, and Schmidt, they first showed that if you take a look at pion nucleon scattering data and make some observations about the S-channel scattering amplitude and T-channel scattering amplitude, then you can categorize the amplitudes in three varieties. The first one being what are called the dual resonance models. The second one are called field theory models, and the third one are called interference models. So what are these models? I will talk about in general in brief detail next. In this book, Superstring Theory by Green, Schwarz, and Witten, in chapter 1, they mention that although the key model of string theory, that is the Veneziano model, it showed that the duality hypothesis, as Faizan mentioned in his talk, that the duality hypothesis was key for the formulation of string theory and the later developments of quantum gravity and other formulations of string theory. That didn't have enough experimental evidence. So what I will mention, what would be the key goal in my talk is to show you that the duality hypothesis is not a well motivated hypothesis. So in this paper by Dolan, Hoare, and Schmidt, they propose this field theory kind of representation of any general amplitude, in which they give a term called f ray j, the second term f res, and a third term that is kind of a mysterious term, and it shows that this mysterious term is what is required to have a dual resonance model. Now the key ingredient is that this f res and this mysterious term in brackets should cancel each other. If this cancellation, only if this cancellation happens, then we get an amplitude that is a dual resonant model. Otherwise, we don't have a dual resonance model, and we will simply end up with a Feynman diagram kind of expansion. So what are these two different models? So in this paper by Stanley Mandelstam, he showed that these two models basically differ by these representations. The first one is the basic Feynman diagram expansion that we have of sum over S-channel terms, sum over T-channel terms, and a kind of a contact interaction where the particles are basically not exchanging other particles but basically coming together and interacting. The second term, however, led to string theory, as you know. This the second kind of resonance, kind of amplitudes are basically what are called dual resonance models, where this bracketed term exactly cancels out the other term, and we are left with only a single channel expansion. And because of crossing symmetry, we see that the S channel expansion is equal to the sum over T channel expansion. So one such model is the superstring amplitude in type 1 string theory. It is a modification of the Veneziano amplitude, and we see that it is a dual resonance model, similar to what we show that if you write a ratio of gamma functions in this manner, then it will be a sum over S channel poles and T channel poles. And the crucial bit is that this summation is equal to the other summation. So if you have a pole in S channel, then it should be reproduced by the sum over all the T-channel resonances as well, provided if it is an infinite sum. if we truncate, then we will not be able to produce the S-channel pole by using T-channel polynomials. Now this weird thing in brackets, this weird thing in brackets is called the Pochhammer symbol. This Pochhammer symbol is basically nothing but a polynomial in X if n is a non-negative integer. So far we have a superstring amplitude that can be expressed as a dual resonance model. But the problem with the dual resonance model is that so far it doesn't have any field theoretic underlying mathematical structure. It is simply a model that doesn't even converge everywhere. So this model is only convergent only if we have t less than 0 and s less than 0 in the complex ST plane. So we needed a representation of an amplitude, of this amplitude, that had this Feynman diagram kind of expansion that had this S channel, T channel, and this contact term. Plus, it had to satisfy the condition that it should be analytic everywhere in the ST plane. And this was proposed by earlier this year in this PRL by my supervisor Aninda and Arnab. So the key ingredient that went into this is that you have this parameter lambda here. As you can see, this lambda comes from a field redefinition. So what is a field redefinition? It is basically if you have, suppose, an interaction in the Lagrangian of this form. It's not working. Anyways, so if we make a field redefinition to psi going to psi plus lambda phi 1 phi 2, then you can see that you get additional interactions in this of this form, right? Now if we make a calculation of the amplitude using this, you see we will see that the amplitude remains invariant, but you get this additional term in the amplitude. But the crucial part is that if we sum over all the modes, sum over all the higher massive modes, then this truncation, this lambda dependence should die out. But it will be lambda dependent if we truncate this sum. So this is the crucial motivation. Now we come to our ansatz for the bootstrap. So crossing symmetric parametric representation means the representation should be crossing symmetric. It should have this one parameter ambiguity lambda in present there, and moreover this representation should have the correct requirements for bootstrap. So it will have these coefficients called the CLNs. These CLNs are the primary ingredient that goes into the bootstrap, and these CLNs have to be positive for unitarity. And also we have this crucial bit that this left hand side of this equation will be lambda independent, and the right hand side, although it has lambda dependence here, but if we have an infinite sum over n, this lambda dependence drops out. Okay, now we come to the thing that we minimize for bootstrap. We need some physical principle for bootstrap. We can't just use arbitrary things. So let's see. So for that we use this thing called entanglement minimization. What are we measuring the entanglement of? So consider tree level 4-point color order scattering. I mean, I know these are many words, but these are basically gluons in 10-dimensional supersymmetric Yang-Mills theory. So these are kind of cousins of the regular gluons that we know, but they have very similar properties like helicity and spin and all that. So if we measure the linearized entropy of this subsystem, so suppose we have particle A and B, and they together form this Hilbert space HA cross HB, and then we measure the rho AB, the density matrix of that particle of that system, and we trace over the degrees of freedom of particle B. We end up with rho A, which is the density matrix of particle A, and then we trace again over rho is squared, and then we get this quantity called linearized entropy. The scattering amplitude in this theory, in this super-Young theory, is given by this. So here G square is the coupling. This F4 factor is basically a factor of polarizations and momenta. We don't have to worry about that. You just have to know that this factor in the forward limit goes as S squared, okay? And then we define the entangling power. The entangling power is basically the difference of linear entropy of the initial and final states. If the initial state is a product state, then the entanglement is 0. So basically we measured the entanglement of the final state, and that is given by sum over residues of the amplitude times the delta function. This residue counts because we are measuring the imaginary part of the amplitude, and that basically gives us this delta function that is associated with this residue. And if we integrate about the delta function, we remained with this simple looking form, that is this Gegenbauer polynomial times these coefficients, the partial wave coefficients that are to be found out using the bootstrap. It's basically the helicities. The helicities is the particles. So spin up, spin down. So the prescription is that we have an amplitude, we are minimizing something, we are imposing some constraints like unitarity, analyticity, and crossing symmetry, and then we find the results. So if you do this for the superstring amplitude and fix the Wilson coefficient W10, so what is the Wilson coefficient? It is if we expand the amplitude in a Taylor series expansion about S plus T and ST, which are crossing symmetric combinations, then the low-lying coefficients of this Taylor series expansion are called the Wilson coefficients. If you now fix the Wilson coefficients to some values, for this case we are using the superstring amplitude, so we are fixing it to minus zeta 3 and this 7 pi to the power 4 by 360. These are some arbitrary values specific to the open superstring. Then we see that the bootstrap result and the analytic answer match exactly. So the key insight here is that so these Wilson coefficients are some low energy data. If you fix only the low energy coefficients, then the amplitude will match up to some, say, 2, S1 equal to 2. To match this amplitude exactly up to say 20 or something, all the resonances overlapping with each other, we need the derivative constraints. Those are crucial, and we had to impose them a lot. I mean, like 180 constraints for a single derivative, and it took like 1 hour anyways. So these are my results. This is the leading Ricci trajectory. This is the subleading Ricci trajectory. You can see that we have excellent match with the upper superstring values for CLNs. All the results match the exact, and the bootstrap match exactly. And so now, so far so good. We have the open string results all matching very nicely. But what we are after is going beyond dual resonance. We want to show that there exist amplitudes that do not follow the duality hypothesis at all. So for that we take, so where did the answers go? Yeah. So here you see this red line. This actually is crucial for this to go beyond dual resonance. This line is basically the open superstring ansatz, but this line, this red colored, is basically what will lead us to go beyond dual resonance. Okay, so what is this plot? So now we don't have the Wilson coefficients fixed to some superstring. We vary the Wilson coefficients over an entire space of Wilson coefficients, and we find out the amplitude for each of those points, and we plot the duality measure. There is some duality measure, a mathematical formula, but that I'm not showing here. And this heat map is basically showing the duality across this entire space. So you see this one point is basically string. This entire space of the S matrices are all different S matrices that are valid S matrices, and all of them don't necessarily show the duality hypothesis to the maximum. However, the string is in the blue region, so string is dual. Next there comes this plot. This is the crucial bit. See, this string again is in the blue region, but there are other S matrices which have W10 negative, which are black star, which is represented by this black star amplitude, and this is exactly the amplitude that we are looking for. So for the black star amplitude, as you can see, in the forward limit, where when t is very small, this black star amplitude is actually decaying. So it actually satisfies duality in the forward limit. But you see, when we go to some higher magnitude of t, this black star amplitude that we showed in this plot, this amplitude is actually going to a constant. This doesn't decay. So this is a clear proof, and this is numerically, although done numerically, but this has convergence in both the number of parameters and the constraints. So this shows that the duality hypothesis is not a valid, is valid for all kinds of S matrices that we can study. So thank you.
Thank you, Debapriyo. And now it's open to questions.
The one which you are using, this Veneziano one?
Yeah, but okay, but
so how are you calculating the entanglement?
All I'm using is that this helicity, these factors F4, this F4 factor has some polarization. This F4 factor has polarization and the momentum. And we are only taking the forward limit of this F4, and that gives us this factor S squared that is required to calculate the first finite moment of the entangling power. So this entangling power is not always convergent, this sum. So you have to take this S squared in the denominator for this to be convergent everywhere.
Okay. Yeah, that question which I asked for the previous talk,
Right.
I mean this thing about zeta 3 and zeta 4.
Yeah.
So suppose you relax that, where do you go? I mean,
So if we relax that, we get this entire plot. So this is basically zeta 3 and zeta 4. So zeta 3, this is, but if you relax that, we get this entire space of S matrices.
So
all of these are convergent.
How much did you vary, zeta 3 and zeta 4?
So this is like minus 1.4 to 0, and this is 0 to 2.5. So this is zeta 3, which is kind of minus 1.2 and 1.9.
But you can, of course, you can vary anywhere, right?
So because of so there is a crucial thing called low spin zero dominance in string theory. So because of spin zero dominance, we cannot go negative in both W10 and W01. So it's you are restricted to some quadrant, and also this. So in that quadrant also only the half of the quadrant is spanned. The rest half is excluded.
So this is an upper bound for this 2-point.
Exactly, this is the upper bound of the 2-point amplitude, the 4-point amplitude. Similarly, there are for other theories we don't have this dual resonance imposed on from the start. We have both lower and upper bounds, but the lower bound includes negative W01, which was not present in this kind of theories.
Okay, once again, thank you for the nice talk.